In this section, we're going to introduce topic modeling and how this unsupervised learning technique allows you to use semantic information when you make recommendations about content. So we'll take a look at the various approaches to text and topic modeling, and then dive into implementation by first looking at how you need to prepare your data for this task. We'll run several of the algorithms that tend to perform well in this field, and take a look at how you can tune, compare, evaluate, and also visualize your results. So let's get started with an overview of the evolution of the approaches in the field, so you see how we got to today's current state-of-the-art approaches. So let's see why it is a good idea to try to model topics, and then go from the initial word space models to the current probabilistic models that make up the state-of-the-art and which we'll be also using, and these are in particular latent semantic analysis and especially latent Dirichlet allocation. So why is topic modeling a great idea? We would like to be able to take large amounts of text and to actually organize it efficiently in an automatic way, and to really understand what it means, because then search and summaries become so much more meaningful. And for that to work, it's important to be able to capture semantic information beyond just individual words, because of course meaning comes into existence through the combination of them. So there's always something where the sum is more than the total is more than the sum of the parts. To do this, we need some sort of solution to be able to find, for instance, something like topics that exists but that are not directly visible, or themes that run across documents, because that would allow us to annotate documents in a meaningful way at a higher level above sort of the granular individual words approach. And we can use these annotations then to not only manage but also search documents in a more meaningful way, because maybe the query that we make contains only a few words, but it's really closely related to a larger topic to which a bunch of other words are related. So it would be much easier to actually make good recommendations if we were able to capture kind of these semantic implications and recommend content based on that. So here's an overview of key milestones in the field over the last sort of 40 plus years, starting with the vector space model, introducing how documents can be represented as vectors or simply a sequence of numbers. Moving on to dimensionality reductions or linear algebra approach that tries to uncover hidden latent topics in a lower dimensional space. And then moving on to the probabilistic approach, which is all about trying to really model the process that gives rise to the documents in the first place, which uses then topics as a hidden variable in the process. And then the model's goal becomes to estimate the properties of these various probability distributions. And that statistic approach has a lot of benefits in terms of understanding what is a good model, what is a good fit, how good does the model fit in the first place, and so forth. So the starting point for all of this is the term document matrix, which is a way to take this very unstructured data, right, text sort of sequences of characters with spaces in between from documents, and translate this into a matrix representation where the original documents translate into this sequence of individual terms that make it into that matrix, which we call this back of words model. So we take everything that is in the text and just extract the unique terms, maybe select a subset of those that are more meaningful, and stick them into this matrix, where the entries then tell us whether a given term was present in a document and potentially weigh this presence in a certain way. Of course, the easiest approach is to just do a binary 1-0 representation. We can use the counts of the word in a given document, or we can weigh the presence up or down depending on what the relative frequency of a given term is across the entire corpus of the set of documents, for instance. The important takeaway here is that this allows us to take documents and represent them as a sequence of numbers, which makes them all elements in a space. So there's a geometric aspect to this, which gives rise, for instance, to distance between documents, or directions into which they point, and how similar or dissimilar these representations make these individual documents in this new type of space. So in practice, the challenge is that we have a very large number of unique words. These are all the unique tokens, which is what the individual terms are called, that make it into this matrix, whereas each individual document only contains a very small subset of those. And so if you look at Wikipedia, in English we have several 100,000 individual terms. Of course, each individual document only contains a few hundred or thousand at most. The one approach to make this more manageable is to reduce so-called stop words, which are just common words like is, the, and, and so forth. But also put in thresholds and reduce or exclude words that are either too infrequent or too frequent. Another approach is to use stemming or lemmatization, which essentially reduces words to their common roots. So, for instance, verbs get reduced to their sort of common roots, especially in lemmatization, which takes into account irregular verbs and applies grammatical rules, whereas stemming is a more sort of brute force approach that simply takes a given set of endings and sort of just chops them off. But all of this has the effect that the number of unique tokens becomes less and the length of these vectors becomes somewhat shorter. The benefit of having this vector space model is that since we now can represent documents in the space, we can do the same with queries. So we can map document 1 and document 2 and all others in this higher dimensional space and then translate the query into the same space by indicating which of the terms that constitute this document space or this word space are actually relevant for the query. And that positions the query in relation to all the documents in the space. And then we can use a measure of distance or similarity to figure out what is the document that is closest to this, which in a vector sense means which sort of points in a similar direction. And for this, we could evaluate the angle between the documents, which is typically done using the cosine of this angle, because that can be computed using the dot product between the documents. And since the individual vectors are very sparse, this are mostly empty, that means that the dot product is easy to calculate because most of the factors in these sum products will be zeros. So that allows us to quickly identify which documents are similar to what is posited by the query here. Now, of course, there are some challenges here. First and foremost is the massive dimensionality of this document term matrix, because there's so many terms. And the curse of dimensionality brings with it the challenge to measure distance, because data points become very far apart from each other. And also in a modeling context, predictions become hard because there's so many features. Overfitting tends to occur because there's a lot of noise in there. So in addition, the sparsity of this matrix means that the similarity measure can be very noisy because not all of the words are really meaningful, and overall this just makes things a little harder. So in addition to these kind of technical aspects, there's also a lot of information that gets lost along the way. One is a fundamental problem or challenge or shortcoming of the back of words model per se, which throws away information about word order. But it's also harder to convey, or literally possible, to find out which words are similar in the sense of synonymy or polysemy. So these measures of similarity, they don't capture that several words actually mean the same things. So they're synonyms, or that they are that one word has several meanings, which is what polysemy is about. So these are not accurately captured in a meaningful way by the directions into which these vectors point. And that is ultimately what gave rise to these topic models, where we want to capture these specific attributes by also dealing with the dimensionality problems, because there will be much fewer topics than terms in the world. So our first approach to this topic modeling challenge was latent semantic indexing. The goal here was to find so-called latent or hidden topics by decomposing the term document matrix, which means we want to represent it by several factors. There's a common technique for this, singular value decomposition, which we can use to truncate this factorization, which means we only select a subset of the number of dimensions used to represent it. And we start again with our document term matrix, here represented as row vectors, each document, where each column represents a given term in this universe. And we decompose this document term matrix as three matrices, three factors that are typically called U, sigma, and V, the later transposed in this decomposition. And their specific content. So the first and the last, the U and the V matrix, they contain so-called singular vectors, which are orthonormal vectors. So they are all orthogonal to each other, and they all have length of 1. So they are in the columns of the U matrix and in the columns of the V matrix, which is here transposed. So in this representation, they are in the rows. And then in the middle, we have the sigma matrix, which contains the singular values, which are only on the diagonal, is otherwise empty, so it's a diagonal matrix. And now we can use this matrix, this decomposition, to find what is the best lower rank approximation. So here comes dimensionality reduction. So instead of using the full rank of this matrix, which may be the smaller of m or n, so typically m, we're going to compress this and reduce the number of dimensions and selecting only k. And we can do this by taking only the first k columns of U, which gives us then, which transposes or translates this representation from document term space into document topic space, because this reduction to only k dimensions of these matrices is meant to represent the k topics which live in this lower dimensional space. Similarly, for the sigma matrix, we would set the k smallest, we would only keep k of the singular values and set the others to 0, and we would then also cross out everything but the k first rows of the V matrix, which gives us an expression of the term to concept similarity. So we have documents, topics, and terms and concepts. So terms, concepts, and topics mean the same thing in this here. So since the first U matrix has document number of rows, it now represents these documents with respect to their similarity in regards to the various topics that we have now discovered by reducing the dimensionality to only k. And so this constitutes a mapping, a linear mapping of the original document term matrix to a document topic matrix, and then a term topic matrix in the end, which allows us to cluster and compare these two constituent elements of our document term matrix in this topic space.